Okay, hello from Switzerland. Welcome to our webinar, AVM, the basics of adaptive ventilation mode. I'm Christian Remus, I'm product manager of the bellavista, and with me is Janessa Ratazzi. She is producing and making all these things work. We have all the technical wizardry we have here at the moment. Today I'm talking about AVM, ventilation mode, which is around 3 years now integrated in every bellavista as a standard mode. And this mode I get from time to time, or during all the times over the year, always question about how to use AVM, when to use AVM, what's so special about AVM. And so we start today with the basics, but this is planned as a little serial, and we will have my next webinar with the second part, which is more using AVM strategy and when not to use. So today we're just talking about how it works and what is the theory and the strategy and the algorithm behind AVM. Okay, before we start, for all those who are using a webinar tool the first time, it's quite easy. You have on your side panel of your computer or your laptop, you have this panel, and you can chat anytime. You can just write a comment and type it in on the side. If you want to raise your hand and just have something to comment, you can do this, and we will answer, or we can answer right away. You can do this window to full screen with this button. You can hide this panel and have more screen, or you can ask questions directly over your headset with audio. You can ask questions anytime. I'm trying to look at the screen from time to time, and so we can maybe answer and have some interactive. At the end of the presentation, I'm ready and open for all the questions I couldn't answer during the webinar. When talking about adaptive ventilation, I get a lot of comments. Yeah, I'm not totally convinced about adaptive ventilation because this is somehow something the ventilator does without my control. I don't have the control over the ventilator. I am not the master of the settings, and the ventilator is kind of a black box doing something I don't understand. And when I'm not understanding what the ventilator does, I don't like it. But we have adaptive ventilation in the daily use, because the first level of an adaptive ventilation is already setting a PEEP. The patient on a CPAP will have a CPAP level or a PEEP level. And if the activity of the patient changes, the muscular activity of the patient is changing, the flow will change, and so there has to be an adaptation of the PEEP. This means that PEEP is already the first level of an adaptive setting, of an adaptive control. So all people who are using ventilators day by day are already somehow in contact with an adaptive kind of setting. On the second level, we have PRVC, which is pressure regulated volume control, and we can summarize this under target vent, autoflow, APV, and whatever is in some abbreviations, but the meaning and the working principle is always the same. We have a patient, the lung mechanics of the patient will change, and the ventilator keeps the set tidal volume by adapting the inspiratory pressure. This means whatever the patient is doing, however the patient is positioning, the inspiratory pressure is changing while I'm still setting tidal volume and the respiratory rate. So there is just the adapting in inspiratory pressure. And to give this a name in a special taxonomy, those modes are summarized under adaptive target ventilation. We have a target, And the way this target is maintained is an adaptive way. But there's also a third level, and now we come finally to AVM. AVM is adaptive and also a closed loop control. This means there is a patient. The patient requires a minute volume. This is already the main difference we have to the adaptive target ventilation. We are not setting up tidal volume and the respiratory rate. We are just setting up a minute volume, because the minute volume is necessary to keep the CO2 stable. So I'm just setting, the patient is in need of 7 liters, for example, of minute volume, and I set exactly this minute volume with AVM. Then the lung mechanics, the breathing activity of the patient is changing, and this means that we have an adaptation not only by inspiratory pressure, we have also adaptation by rate and I/E ratio. That means the minute volume will be kept stable, but how the ventilator achieves this is depending on the lung condition or the lung mechanics of the patient. And the ventilator decides what's best for the patient, deciding breath by breath through an algorithm. So how does this work? Sorry, first we have to give it a name. And this is not adaptive target ventilation, this is an optimum target ventilation, because the ventilator is always looking for the optimal way of ventilating the patient. The benefits of AVM are short. We have a continuous adaptation of ventilation, so the patient is always observed by the ventilator. This results in quicker weaning, and also you have less interaction, you have less manipulation. It controls the ventilation and also the timing, so I don't have to set here the tidal volume or the respiratory rate or the I/E ratio, because the patient is always observed by the ventilator. The only thing I have to look at is the CO2 level and the set minute volume. And of course, during AVM ventilation, the patient can breathe at any time he wants, and he can set the ventilator from spontaneous to mandatory, mandatory to spontaneous, just depending on the patient's activity. And so you see, on a regular mode of ventilation, usually patient from intubation to extubation will have a controlled mandatory ventilation mode, and then it will be switched to SIMV or pressure support ventilation modes. And if the patient is stable enough, you will switch off everything and have a spontaneous breathing trial, and then extubate the patient. You can have it much more easier using AVM, because you can just keep AVM from in to extubation and just do not leave this mode. It's possible to ventilate during the whole process, doing a spontaneous breathing trial before extubation and then extubate the patient. So this makes life much more easy. There's a question now for you all, and this question is, which parameters are mainly responsible for the CO2 regulation of the patient? It's possible that several answers are correct, and please answer. These questions. So there are first votes coming in. We're still collecting, and looks good so far. And just give it a guess. It's not a test, it's just how to make it more understandable what AVM is looking after. So we are still collecting, but now I think the result looks more and more clear. Okay, we have a countdown, only a few seconds left. And I think now we're ready and we can submit the result. Okay, so to make it more even, everyone gave every possibility a chance. PEEP 11%, inspiration pressure 33, I/E ratio 56, rate and tidal volume around 70%. PEEP and I/E ratio are mainly responsible for the oxygenation of the patient. If you set and raise and increase the PEEP, the patient will change mainly his oxygenation. The same with the I/E ratio. If you change the I/E ratio, mainly the oxygenation of the patient will change. Of course, in certain conditions with the I/E ratio, sometimes the CO2 is a bit involved, but not mainly. These are the three correct answers: the inspiratory pressure, the respiratory rate, and or the tidal volume. This means everything of these three parameters at the end are resulting in minute volume. And this is what AVM mainly does if you control the minute volume. You're looking for the CO2. You have to set your PEEP and you have to set your FiO2 manually, but everything you do with the minute volume is mainly for the CO2 management of the patient. And how does AVM do this? We see that we type in the ideal body weight. And in this is also a formula for the dead space calculation, why the dead space is estimated. I will come to this later. And we have, for example, a male patient with 1,65 meters of height. This means this is an ideal body weight of 61 kilograms. And now we come to the percentage of minute volume button, and for most of the users, the percentage is something confusing because no one is really understanding why is it percentage, why can't I write an absolute value here. Just replace this percentage with 100 milliliters, so then it's much more easier. So because this is the control which sets the minute volume, and this means I have a patient with 61 kilograms, and this patient is ventilated with 100 milliliter per minute per kilogram. And this means, at the end, 61 times 100 is 6.1 liter per minute. And this means if I go up to 110, this will be 10% more, 6.7. If I go down 10%, it's 90 milliliters per kilo. This will be 5.6. So this percentage can be easily replaced by milliliters per kilogram per minute. And this gives the amount of minute volume which a normal patient, which is healthy, will have during the minute to have a stable CO2 household. It depends if a patient is hypothermic, this must be a less minute volume. If the patient has fever or is septic, this must be a higher minute volume. So you're just regulating the CO2 over this button. This is your volume control and your CO2 button when using AVM. Okay, talking about minute volume. It sounds very striking now, and yeah, easy minute volume, that's fine. I said 7 liters and everything should be fine. But 7 liters can be applied in several ways. We could have 5 breaths with 1200 milliliters. This doesn't sound too good. We could have 15 breaths with 400 milliliters, sound much more reasonable, but maybe it's also not correct. Or you could have a respiratory rate of 30 with 200 ml. So there must be something smart to control this and to make the settings reasonable. This is now where we come to this, what some people might think this is a black box, but it isn't. Because now we're coming to this optimal target. This what is the significant feature of the AVM mode, that during this Otis equation is just relying on the lung mechanics of the patient and is calculating the point of least work of breathing. And this results in a special target rate. That means if the patient has a lung condition, normal, healthy, the Otis equation will calculate a rate where the patient is ventilated with the least work of breathing. And this, for example, could be a target rate of 15 for this moment. I also typed in my minute volume, this may be 6 liter. So now 6 liter divided by 15 will result in the tidal volume. This means this would be a tidal volume of around 400. And so this is the optimum target for this patient. And this is now changing from breath by breath. And this is the highest goal of the AVM, just looking for the optimal target with the set minute volume the user has chosen. And now breath by breath, and you don't have to care about what would be the optimal rate for this patient and what would be the optimal tidal volume for this patient, because AVM and the Otis equation is doing this for you, and it's important for you to know that it's always looking for the best point and the least work of breathing for this patient during ventilation. So AVM is the pressure-controlled mode, but with an optimal target control. You see here is the Otis equation. We have the work of breathing, and this is divided in two players. The one player is the compliance of the patient, and the second player is the resistance of the patient. You see the curve of work of breathing, and there is one point where the lines cross, and this is the optimal point with the least work of breathing. And this is what Otis is looking for, or was looking for 60 years ago, or more than 60 years ago. And he was just looking how do mammals, humans and animals breathe, and he found out that they're always looking for the best point of and the least work of breathing to be comfortable. And of course this changes when the lung conditions are also changing. That means if the patient gets ill, breathing gets more exhaustive and will be not so easy when you have a restrictive or obstructive problem. There are also some lung protective rules, because now we found the optimum target, we found the optimum point for the least work of breathing, but patient has to be safe. And so there are 4 rules, and this is on the AVM graphic, the window around the curve. And what do these mean? This means there is one which is set by the user. This is the P limit. You decide as user how high the limit, the pressure limit for this patient should be. That means if usually following some protocols, you should limit it to a value around 30 centimeters of water, just to be in a lung protective area. And this is the only setting you can really control on AVM regarding the lung protection. This means you are responsible to find a reasonable setting, and this should be, I think, around between 30 and 40 centimeters of water to have a lung protective ventilation strategy or following a strategy. And the other values on this window you can't control totally, but maybe a bit. The second one is the minimal tidal volume. At the beginning, we set in the height, and the height was also calculating the dead space. And that means I have the 61 kilo patient, and the dead space is 2 milliliter per kilo. That means this patient has around 100 and 125 milliliter per kilo dead space, anatomic dead space. And this will be taken times 2. That means the minimal tidal volume for this patient won't be under 200 ml. So that means AVM prevents dead space ventilation. As soon as the tidal volume drops below 250, AVM will either raise the inspiration pressure or find some ways to get the tidal volume above 250 ml. The maximum rate is the expiratory time constant. That means the AVM mode is measuring the expiratory time constant. How long does the patient need to exhale? And this means that no auto PEEP can be developed under AVM, so the patient is always exhaling what he already became from the ventilator in the inspiration phase. So when I have more or longer time to exhale, the maximum frequency will be lower, because when I'm an obstructive patient, this means that the patient can't breathe 60 times a minute, otherwise he would develop an auto PEEP, and this will be prevented by AVM. And the fourth will be just the minimal rate, because you don't need a dedicated backup ventilation for AVM, because as soon as the ventilation or respiratory rate drops in the area of 5, the mandatory ventilation will step in. And this is the protection frame, and as long as the patient is inside this frame, he's ventilated and protected by the safety rules, so the patient ventilation will be safe. You can also use this graph to estimate the lung condition and lung mechanics of the patient. As I said before, if I have an obstructive patient, means this patient needs a lot of time to exhale because he's obstructive. And this results in a low respiratory rate. And this means the window will be not square, it will be rectangular, and the maximum rate will be very low. In this case, it's around 12 breaths per minute. And this means to prevent auto-PEEP, the maximum rate is 12. So this is not much. And AVM is just adapting to the lung mechanics of the patient. The opposite is restrictive patients, patients with pneumonia, with ARDS. You have lots of difficulties to get air into these patients, but it's very easy for them to get lost of the air, so they don't have problems with their expiratory time constant. And this means they can be ventilated with low tidal volumes and a higher respiratory rate. And as soon as you pass a ventilator with this graph, you could always see at a glance the lung condition of the patient. If it's a vertical rectangular shape of the lung protection window, mostly it will be an obstructive patient. It's a horizontal rectangular shape, it will be a more restrictive patient. So it's very easy to follow the lung conditions when you're using this window. I already spoke about this. We have a set percentage of minute volume, and if I will increase the ventilation because my CO2 is too high, I just set the percentage or the milliliters per kilogram per minute up to 10% to 20%. We will talk about this more specific in the next part. Or I decrease the minute volume when a patient has hypothermia or a low CO2. Or I will start my weaning course and just want to make the patients a bit more starving of minute volume to stimulate him starting his own spontaneous breathing. And now we see we have our 6.1 liter patient, and I set this minute volume to 120%, and this means he's not getting 6.1 liter anymore, now he's getting 7.4 liter anymore. And all will change, the protection window will change, the respiratory rate probably, or the tidal volume will change. I don't have to care about this. Usually I have to think about what to change, either the rate when I'm doing it manually, or the inspiratory pressure, or the volume. And here it's a very luxurious and comfortable thing to just say, I need 8 liters, please ventilator, do this for me. And I can be sure that he will do it with the least work of breathing. So to summarize that's how AVM is working, your starting point is always the patient height. This is very easy. You can measure the patient, you can look in the patient data, and then you set it, and the gender should also be set too. Then I will start the ventilation. At the beginning, AVM is doing initial 3 breaths just to measure out the lung mechanics. And then maybe 1 hour later, 30 minutes later, I have to check the CO2 of the patient, or have a mainstream sensor and can check myself. And then I decide, okay, should I increase the minute volume, or should I decrease the minute volume, or should I leave it like it is? Of course, still, that's given. I need to adjust PEEP and FiO2 for the oxygen regulation and for the oxygen situation of the patient. For safety, the lung protective rules will always be there and active. But remember, setting the PEEP limit is your responsibility, and you have to find reasonable settings for this to be lung protective. And spontaneous breathing is possible for the patient at any time, from the beginning, at the end, whenever he wants to, and when the patient is getting tired, weaker, the mandatory ventilation will step in. There are also some contraindications for AVM, just to talk about them at the end, because otherwise everything would look too perfect. The expiratory time constant, which is called calculating nearly everything in AVM, is very sensitive to leakage. So I can't use AVM during non-invasive ventilation because this value can't be calculated too reliable. So I have to take out non-invasive ventilation or ventilation with a very high leakage. Patients who have pathologic breathing patterns, as you see one right in the graph there, this is a changed Stokes breathing patient, or hiccups will be detected as triggers, and if a patient has one hiccup per minute, that's no problem, but if he's constantly having hiccups, this will confuse AVM, so all these patients are not suitable for AVM, and neonates below 5 kilos shouldn't be ventilated too. So these are the 3 contraindications, but there's no contraindication regarding ARDS, COPD, or any other lung condition. Those all can be ventilated with AVM. But how to ventilate them, and some strategies and some traps, this will be discussed and shown in the next in the next webinar. So